Welcome back, viewers. This is the second part of differentiation. In this video, we are going to derive the Newtonian method, or the first method of differentiation. So let's get going. As a recapitulation of the previous video, let us recall what we derived. We derived that when delta S and delta T tend to 0, then delta S becomes ds and delta T becomes dt. And our instantaneous velocity becomes ds by dt approximately. But the question is, can we represent this situation on a graph? So let's derive. We know that in a graph, the function of x is always y and the function of y is always x. In this case, let us consider a displacement time graph in which x is time and y is displacement. No, that was not the graph. We need a graph with function of x equal to x square, which is equal to y, where x is time and y is displacement. How would it look? Yes, it will look like this. Now, if I tell you to find the instantaneous displacement at delta t, then will you be able to find? Yes, that's differentiation. Now suppose, for example, let us consider 2 points x and x dashed on the x-axis. Now, as we know that the function of the graph is that function of x is equal to x square, then function of point x is y on the y-axis, which is the value of x square, and value of point x dashed on the y-axis would be y dashed, which is equal to x dashed whole square. I would request the viewers to agree with me on this point. Think it deeply and then please proceed to the next part of the video. Now, if you have agreed with me on this point, then let us proceed to the next part. We know that to find the rate of change of y with respect to x, we have to apply this formula: y dashed minus y whole by x dashed minus x. Can we represent this formula to represent differentiation? Yes, we can, but we have to modify this formula. We know that y dashed equal to function of x dashed and y equal to function of x. Then the formula y dashed minus y whole by x dashed minus x can also be written as function of x dashed minus function of x whole by x dashed minus x. Now let us consider that x dashed minus x is equal to h. Then x dashed is equal to x plus h. We need to do this to eliminate x dashed, because it is much comfortable for us to work with one variable in one equation. So how can we write the previous equations? A few minutes ago, we derived that function of x dashed minus function of x whole by x dashed minus x is equal to the rate of change of y with respect to x. So we can write it as, wait, at first write the conditions that are required for framing the equations. We know that function of x dashed is equal to x dashed whole square and x dashed is equal to x plus h. So function of x dashed becomes x plus h whole square, which is the function of x plus h. Don't you agree? Please agree this point on with me and proceed in the next part of the video. According to the conditions, we can frame the equation as function of x plus h minus function of x whole by h. Stop! Don't close the video. It has something more. Let's see what's that. Now let's imagine. Suppose h tends to 0, means the value of h becomes very small, and we can see that the 2 points x and x dash are coming towards each other and keeping a gap of very small value between them. Then can't we define this as delta t or h? Let's watch how would it look as whole. We see that in a different time graph, x and x dash converge to each other at a point almost equal to 0, not equal to 0, and the instantaneous velocity of the displacement time graph becomes delta s by delta t, which becomes ds by dt, which is the velocity instantaneous. Thus, we can represent differentiation as limit h tending to 0, function of x plus h minus function of x whole by h is the rate of change of y with respect to x. This was derived by Sir Isaac Newton. Hope you liked the video. Please like, share and subscribe our channel.